Okay, let's start. So we have been looking at the problem of making a negative feedback loop stable, and in the last class we essentially saw that the underlying principle behind the schemes that we'll use is the following. Although we have a higher order system, we try to make sure that the loop gain behaves like a first order system around the unity loop gain frequency at least, right? That's the basic idea. And we saw there are essentially two lines of thought. One is to go and add an LHP0 to the loop gain so that the closed loop poles fall on the real axis. The second is to keep the open loop poles far apart so that for large values of DC gain the closed loop poles will lie on the real axis, right? And in fact, although we saw this as one way to do this, we can also keep the poles far apart by doing something else. I think one of you had already asked me. So let me just draw a two-stage OTA first. So this is the first stage GM1. Say the conductance and capacitances are G1 and C1. This is the second stage GM2. Let's say this is some G2 and C2. So here, where are the open loop poles lying? Yeah, it's clear the two sections are uncoupled, so we can directly write it as G1 by C1 and G2 by C2. And you might know that they might be close by. So our goal is to make sure that the two are far apart, right? So which means I can move one of the poles to a low frequency or to a higher frequency. Which of the two do you think is easier? Pushing a pole to a lower frequency or to a high frequency? How can you push it to a low frequency? Yeah, basically you can put a large capacitor at any of the nodes. That's going to increase that is going to reduce the pole location, right? So let me actually copy this. Okay, yeah, so let us say it turns out that in your application you have a very large load capacitor that you'll add here. Okay. If the load capacitor is so large, then the pole associated with the output node is now G2 by C2 plus CL. And if CL is so large, then this could be much smaller than the other pole G1 by C1. Right? And if this happens, then around the unity loop gain frequency, it will behave like a first order system. And as long as this has sufficient phase margin, you can do this, right? And otherwise also, you can also, So this is not the only way to do this. To make one of the poles move to a very low frequency, you can put a large capacitor here also, right? So here the Cx is so large that the pole associated with that node becomes much smaller than the other pole, then also it's fine. Right? And in fact, sometimes this is also done, and this is typically called the dominant pole compensation. Wherein the idea is you go and put a large capacitor at one of the nodes to make sure that the pole associated with that node becomes the dominant pole, so that once again, if you draw the Bode plot, the loop gain behaves like a first order system around the unity loop gain frequency, right? So if I were to qualitatively sketch the Bode plot, okay, yeah. Let's say this is the magnitude of the loop gain. So let's say it starts from here, and then we encounter the first pole, and then let's say the second pole comes nearby. Without doing anything, this is what we'll have. And as you see, around the unity loop gain frequency, it is like a minus 40 dB per decade slope, not great. So in dominant pole compensation, we don't touch the, let's say, this pole, and move this pole to a very low frequency, let's say somewhere here, right? So when I do that, I'll get something like this. So now you see that around the unity loop gain frequency, this is behaving like a first order system, and if you are able to keep them sufficiently far apart, you can get a good phase margin. Okay. So this is obviously one way in which you can keep the poles far apart, but here we are just pushing one pole to a low frequency, but if you can also push the other pole to a higher frequency, like we saw here, so here this pole moved to a low frequency, this pole shifted to high frequency, this will be even better, right? Instead of just pushing one of them to a low frequency, you also make sure that the other pole drifts apart. So this will be even better, and as you guys pointed out in the last class, this is something we observed due to Miller effect, right? And we actually saw this in the context of in which context did we see this Miller effect? Yeah, in common source we saw this. So let me first refresh that result. Where? Yeah, that is something, I mean, here it is unstable, right? It is not good. So you have to compromise something, right? So let me first draw the common source we saw. This is the input Vin, this is the resistance Rs, and we considered a total capacitance C1 here. And then we had the transistor, which we replaced by a transconductor to make it more generic. I'll do the same here. So this is some GM, and then let us say this is some G0 and C0. So here again, initially if you don't do anything, I mean without considering any other extra capacitor, where are the poles now? Gs by C1, and second pole was at G0 by C0. But as we saw, the moment we considered this CGD, which is the capacitance across the transconductor, so this is basically without the capacitance C. Now if I added this capacitance, where did the poles move to? Or first of all, what is the pole associated with this? The conductance is still the same, but as we saw, the act of putting this impedance across this amplifier can be reduced by using the Miller approximation. Again, if this was a voltage controlled voltage source wherein you know the gain from here to here, you could use it without error, but this is a current source, so we only approximately know the gain at low frequencies. So at low frequencies we do the approximation, and the total capacitance was C1 plus C into the gain and the conductance sources, right? And what about the pole here? Again, if you recollect, if I try to write the total capacitance here, I have C0 that comes in parallel with these two guys in series. So first let me write that. So we have C0 plus C1C. So next job is to find the conductance, and as usual for finding the conductance you apply a test voltage, you find the test current, and in particular you find the real part of the test current. So here this G0 will take away real current, so that will directly appear. In addition to that, yeah, the GM will also draw some current. And what is that current? Or first of all, if this is V test, what is this voltage? Yeah, again for pole calculation this is not there, and at high frequencies RS parallel C1, C1 is dominating, so essentially have a capacitive division between V test and this point, so that is at C by C plus C1 times this. So the current drawn will be GM times this.
And so we are able to figure out the poles by GS over C1 plus C times, like that, considering that the poles are far apart. Another assumption we are taking right.
So here basically what we are doing, two things. One is, it is implicitly assumed that the one pole is at a low frequency, other is at a high frequency. So because the pole associated with this node is at low frequency, that is why we could say that the gain from here to here is Gm by G naught. That is why we could write this capacitance like this. So that's where we have made that assumption. Similarly here, when we say, when we are ignoring Rs with respect to C1, this assume that we are looking at a high frequency pole, which means you don't have to consider this, and it's basically these two guys alone. It is implicitly assumed there that this is at a low frequency and this is at a high frequency. And that's what happens in practice also. Yeah.
Sir, when we neglect the feedback capacitor, can we comment on the P1, P2 value like we will?
I mean, when you don't consider C, they need not be so far apart. I mean, they might not be exactly at the same location. They'll be away, but depends on how away they are, right?
Can you comment like P1 will be less or P2 will be?
Okay, now it is not that trivial. Now it depends on what is the source resistance you assume and G naught you have. So without that information, it is not easy to say, right?
But they are close.
They could be close by. See, I mean, even if they're not very close by, it might not be far apart that it is stable, right? Here you see the two poles have to be sufficiently far apart. This much we can't have. Unless you go and put a large capacitor at some node intentionally, like we saw with the dominant pole compensation, right? Okay. Yeah, so this is basically the common source, and we want to do something similar in a two stage, right? So here you see that this is shifting to a low frequency and this drifts to a high frequency, and this is what we called as pole splitting. And in a two-stage OTA, we want to do something similar. So first let me sketch the two-stage OTA, then you will see the parallel between these two. So this is the first GM, GM1, this is the input. Again, the conductance is say G1, capacitance is C1, and then you have the second stage. And let's say that at the output, we have the intrinsic output resistance that has a conductance G2. I'll also add the load resistance together, and I'll call this as some GL prime. It includes a load resistance also. Similarly, the total capacitance I'll consider here. I'll also club the load capacitor. So it's C2 plus CL, which we'll call as CL prime. So this is a two-stage OT, and here once again, if you don't do anything, the poles are at G1 by C1, and okay. So once again, we want to shift them far apart, and if you see here, I have a voltage source in series with a resistor. I can convert it to current source in parallel with the same resistor. So first let me do that. If I do that, I'll have the current source. What will be the value of the current source? V in by Rs, I'll write as V in times Gs. And then you have the same resistor. Okay. So now you see that what is this current here? It's basically Gm1 V in. So now if you compare the two, you have something similar. Here you have V in times Gs current getting pumped into this network. Here I have Gm1 times V in current getting pumped into an identical network with just labels are different for the conductance capacitance, right? So here we saw that if we didn't have this capacitor, the poles were close by, and the moment we considered this capacitance here, they drifted apart. So here again we have the poles to be close by. If you want them to be apart, what do you do? Yes, capacitor across second stage.
So for analyzing the poles, we will not consider our sources, right?
Correct.
So like we can also say it like this, we can remove that current source.
Yeah, it's open.
Source, like remove that transconductance block from here. If V in is 0, like.
Yeah, this is not there. Correct. Yeah, the same thing. So we'll go and put a capacitor across Gm2, and I'll call this CC, standing for compensation capacitor, because that's an explicit cap you are putting to split the poles. Okay. So once I do that, can you tell me the pole locations now? Okay, let me write. This is without CC. Now I added CC. Where will be the poles now? G1 by C1 plus C into GM2 by, okay, same thing, the existing capacitance plus this capacitor multiplied by the DC gain of this guy. And what about the second pole? First let's write the capacitance. What's the total capacitance associated with the output? Yeah, CL prime plus C1 CC by C1 plus CC, right? So this and these two in series. And the conductance, if I write, I'll have GL prime plus GM2 times CC by. It's the same thing. Whatever was here is what I've written. Just the corresponding labels are changed.
In this case, why we didn't consider the effect of load and load capacitance?
We have considered, right? I mean, I clubbed the load conductance here, load capacitance here. In this case, I mean, let's again assume that it is all added in G0 and C0. Okay.
They are then the same circuit. Then,
No, this is basically a common source, simple common source where you had a source resistance. Okay, if you had to brush your memory, this was the circuit, right? Wherein you considered 3 capacitors here. What I'm trying to say is the moment you consider the source resistance, this kind of looks similar to a 2-stage OTA with respect to the poles and zeros. So this was just to draw a parallel between the two. Is it clear? Okay. Cool. So now, I mean, can you help me approximate this further? Among these two terms, which will be high, do you think? I mean, C1 is the parasitic capacitance you have. You are adding an explicit capacitor CC, and in turn that gets multiplied by the gain. So approximately I can say this as CC times. Now similarly, can you help me approximate this? I have GL prime, I have GM2. Among the two, which do you think will be typically higher? GM2, because you want DC gain of this stage is what? GM2 by GL prime is the DC gain for the second stage, that you obviously want it to be greater than 1. So I can approximate this further as
driving a very low load, then it can be GM2 by GM2.
yeah, but you again, if you're driving a very low load, you design GM2 so that the gain is reasonably high, right? You don't want it to be less than 1, right? Again, this is an approximation. Depending on your situation, you have to use it, right? This is assuming GM2 is greater than GL prime, right? So okay. So in this circuit, in addition to the 2 poles that we have written here, is there something else? I mean, first of all, how many poles we will have here? I can only set 2 capacitor voltages independently, because if I initialize these 2 capacitor voltages, this is automatically defined. 2 poles that we have written. Is there a 0 here?
Yes.
Right, we can short this capacitor. Output is non-zero. And again, intuitively also we have currents from 2 different branches with different phase shifts getting added. And we also computed the 0 here. So let's also do for this, in case you forgot. Let me copy this I'll remove it. Yeah. So we are trying to find the 0. As usual, I'll assume that V out of S is 0. So what is the current flowing, and if I call this as V1, what is the current flowing through the capacitor? V1 of S times SCC. That is the current flowing through the capacitor. What is the current flowing out of the transconductor? Minus GM2. I mean, this is V1 is applied to the inverting terminal. So the current flowing out is minus GM2 times V1 of S. This should be equal to sum of these two currents must be equal to these two, and the currents here are 0. So once again, this means that I have something like this. So we can argue that if input is non-zero, V1 definitely will be non-zero. So the only possibility is for the second term to be 0. So that gives the 0 to be at this location. And this is in the left half plane or right half plane? It's a RHP 0. So do you think this is good for stability or bad for stability? But in the last class we saw, if you have an LHP 0, that sort of gives a time advance, and RHP 0 adds more phase, so we have more delay in the system. So this will degrade our phase margin. We will see how much it degrades. Cool. So let me first summarize the result. So what we have now is typically called the two-stage Miller compensated OTA. So let me quickly sketch it. GM1. So this is GL prime and CL prime. So as you know, we have 2 poles and 1 0. So I can write the transfer function A of S as some DC gain times 1 minus S by Z1 RHP 0 and then the 2 poles. Let's quickly write down the values of all of them. So what is the DC gain A naught? Write it here. What is the DC gain here? Oh sorry, I also forgot to add the Miller capacitor, the compensation capacitor here, right? Yeah. What is the DC gain? DC gain, the capacitors are all open. What is the gain? GM1 by G1. Fine. This is the DC gain. And let's also rewrite the pole locations. The first pole is approximately at, what is the total pole? What is the pole associated with this node? The conductance is G1 and the capacitance is approximately Cc. Yeah, we'll ignore C1 for now. Cc times Gm2 by. Second pole is, first if I write the capacitance, I have Cl prime, this capacitor in parallel with these two in series. And in the conductance, we have ignored Gl prime because Gm is larger, and the component corresponding to Gm is Gm2 times Cc by C1 plus Cc. And once again here, if I make the assumption that the capacitance C1 is much smaller than Cc and Cl, okay, and also I will say even C2 is smaller than Cl, then can you help me approximate this term? I assume that C2 is the intrinsic output capacitance here that we had clubbed it, right? We have intrinsic output capacitance here. In addition to that, we have the load capacitance. Together it is Cl prime. Okay. So C1 and C2 are the intrinsic parasitic capacitors at that node. Cl is the additional load capacitor that we are adding. Together I am calling it Cl prime. Similarly, the intrinsic output conductance we have here is G2. Along with the load conductance, it is Gl prime. Is that clear? So here let me assume that C1 is smaller than Cc. So how will this simplify to? Yeah, P2 is approximately Gm2. And what about the denominator? So this will be approximately what? This will be, no, C1. We have two capacitors, C1 and Cc by C1 plus Cc. I know C1 is much smaller. I can basically ignore this. So then C1, and I'll have Cl prime plus C1. Again, Cl is much greater than other capacitors. Okay. I mean, the other way to see is if basically if I separate the capacitors, maybe then it might be easy to understand. So let us say C2 and I have Cl. I am saying that this capacitance is much greater than C2 and C1. So among these two, Cl is going to dominate, and here if I put these two in series, C1 will dominate. So it is Cl plus C1, which is approximately Cl. Again, this is under the assumption that these two are there. Okay. So this I will say if this condition is satisfied, we can approximate as Gm2 by Cl, and we also have a right of plane 0, which we just computed it to be at Gm2 by Cc. Fine. Great. So now, I mean, what we expected here was the two poles getting split. That definitely happened. One drifted to a low frequency, one drifted to a high frequency. But what is something that was unexpected? Yeah, the 0 was something that we didn't expect. And as I mean, we already know that this 0 being in the right half plane will degrade a phase margin. So let's try to get an expression for how the phase margin is going to look like. Okay. And to find the phase margin, first what do I have to find? Yeah, I have to find the unity loop gain frequency. So first let's do that. Let me actually erase this. So again, let's assume that the feedback factor is some beta. So my loop gain is beta times this entire thing. To find the unity loop gain frequency, I'll put S as j omega, equate the magnitude to 1. The mathematician in you will be very happy, but the engineer in you should feel ashamed, right? Because you solve it, you'll get big expression, but we are engineers, we try to get a practically usable result. Okay. So one thing we'll assume is the following. See, finally when I add this capacitor Cc and do the compensation, what can you say about the loop gain around the unity loop gain frequency? It's behaving like a first order system. So if I qualitatively sketch the loop gain's magnitude plot alone, it's starting from the DC gain. I know one pole will be at a low frequency now, and then it will behave like this. So this is my omega u loop. And what can you say about the second pole? It is going to come before omega u loop or after omega u loop? After that. So it's going to come sufficiently after this, and the 0 also will come later. Right? So this is what you want typically, right? If this is the case, how can I approximate my loop gain to be? Yeah, I mean, okay, like this, right? I mean, yeah, it's also correct, A naught into S by P1, right? The point is I'm approximating like a first order system once again. So this is true for, I will say, well compensated OTA. Okay, that is, by well compensated I mean that we have within quotes sufficient phase margin, that is the second pole is occurring at a higher frequency than your unity loop gain frequency. Right, this is what you would want in practice, and so let us say we do this. So then this is the expression at least till omega u loop, right? Till omega u loop we can approximate like a first order system. So now for a first order system you very well know what is this, what is it? Beta times A naught times P1. So you have everything, A naught is here, P1 is here. So what is the product of these two? So Gm2, these two goes away, these two go away. What are you left with? You'll have beta times 1 by Cc. Okay. So I'll write it here, unity loop gain frequency, or first I'll write omega u as gm1 by Cc. By omega u I mean that we are only taking the open loop gain A of s and finding where it goes to unity without the feedback factor, right? And that will be at gm1 by Cc. With a feedback factor of beta, this will be at omega u is only for A of s. I am just following this notation to clearly distinct the two. Okay. So A of s is basically this without beta, and that goes to unity when at A0 times P1. The loop gain is beta times A of s, and that goes to unity at beta times this frequency. So, cool. So now you know omega u loop. Let's try to find the phase margin. I can have it maybe. So I am trying to write the phase. For finding phase margin, what should I find first? I should find the phase at what frequency? At omega u loop. So let us say I find this. This is going to be the phase contributed by each of these guys at omega u loop. What do you think the phase contributed by the first pole? Look at the plot here. We have something like this. The first pole is occurring here. It is occurring at a frequency much lower than your unity loop gain frequency. So the moment you reach this point, what do you think will be the phase contributed by P1? Till approximately reach minus 90, right? So I don't have to worry about it. So it's minus 90. For the second pole, we don't know. So we'll write the exact expression. Tan inverse of omega u loop by P2. Right? And what about the phase added by the RHP0? Minus or plus? Minus tan inverse of omega u loop by Z1. And you have the value of both omega u loop and Z1 here. What is the ratio? I'll write it here. Help me complete the expression. So P2, I'll write it as such. If I take the ratio of the unity loop gain frequency and the zero location, what do I get? Yeah, you'll find it's beta times gm1 by gm2. So this is the phase at the unity loop gain frequency. So what is the phase margin? Yeah, 180 minus the mod of this. And what is that? I'll have 180 minus magnitude of this. Basically I'll not take the minus, right? So you'll have, yeah, tan inverse of the same thing. Okay, this is the phase margin. Is it okay? So to get a good phase margin, the phase added by the zero should be smaller or larger? The zero, you want it ideally to add zero phase. So you want the phase added by this guy to be very small. So then can you comment on how we might choose the ratio gm1 by gm2 to be? You want it to be very small, right? So this gives you a first design choice. You typically choose your gm2 to be greater than gm1 to make sure that if you have the RHP0, the phase lag due to that RHP0 is not so much. Okay. And secondly, what can you say about P2 location with respect to the unity loop gain frequency? This has to come much further away from the unity loop gain frequency. So that's the key thing. Again, the idea is you want to make sure you have a first order behavior. So in the first order, the second pole is theoretically at infinity. So you also want the second pole to be at a much higher frequency than omega u loop. So this is something you want. Okay. and you choose it based on the required phase margin. And in a couple of classes back, we saw that you typically choose phase margin based on two criteria. One, let us say you want fast settling, then you make sure that the closed loop poles are critical damping. Basically, you have two, in closed loop you have two poles, you want them to be on the real axis, but if you recollect, we didn't want them to be on the real axis away, you want them to be on top of each other so that the settling is fastest. So that again I'll give it an exercise, the phase margin corresponding to that will be 76. Or if you want to, if you look at the frequency response of the closed loop transfer function, if the phase margin is low, you will see a lot of peaking. Again, we saw in the couple of classes back, I don't know if you recollect. Yeah. So here if you recollect, we saw if the phase margin is smaller, if phase margin is 0, you'll have infinite peaking. This is corresponding to 45 degrees. And if you want to make sure that it doesn't peak at all, we aim for 60 degrees. Okay. So you can either choose it to be 60 or 76 degrees depending on what is feasible, right? Great.
So while designing this two-stage, wasn't the whole point to sacrifice the gain of the second round so that you have a higher gain over?
Correct. Gain of the second stage you are sacrificing, but you don't want it to be less than 1. I mean, the point is if it's less than 1, you are losing the overall gain.
Right, but in this case you're making G2 greater than G1, so aren't you sacrificing?
No, we are not making G2 greater than G1. Where did we assume? GM2 is greater than GL, right? Where have we written? Oh, GM2 greater than GM1, right? GM1 is the transconductance of the first stage. I mean, okay, if there's a confusion. Yeah, it is just a this is GM1, right? The first stage, whatever short circuit transconductance you have, that is GM1. For the second stage, it is GM2, right? The idea is you make the transconductance of the second stage greater than the first stage if you don't, I mean, if the zero is there, okay?
What's the product GM1, GM1, G1 and GM2, GM1?
Yeah. This is the product.
Yeah, so that first term.
Oh, you are saying, I mean, see, the point is if I increase GM2, we'll see how to increase GM2. That will also correspond, I mean, basically, you try to keep this same. Right? You increase GM, you also make sure this increases so that the gain remains same. Right? That's what we'll do. Okay. So we'll see how we'll scale it later, but yeah. So let me, okay, we have some time. Let me do the following. Let's quickly do a small example.
So how do we choose the value of beta?
Depends on the application, right? It is a final. It is determined by where are you going to use this finally, right? In the closed loop thing, whatever you have as beta, that's what will be beta. Okay, so let's take a small exercise. So let's say you are given a particular load capacitor and you want to make sure you get a particular phase margin at a given unity loop gain frequency, and feedback factor is also known. Okay, so these are all given. So let's say we want to design this two-stage OTA at a system level. That is, I essentially want to find GM1, GM2 and the compensation capacitor CC. Okay. So how do you think we can proceed?
We know omega u loop, that's
Yeah.
GM1 by CC.
Okay. You know omega u loop. Omega u loop is beta times GM1 by CC. We don't know GM1, we don't know CC. Okay, let me copy phase margin expression. So we are also given phase margin. Yeah, in phase margin, omega u loop is known, but you don't know P2 or this ratio. What can we do? See, once again, this is how things will be in practice, right? You'll have more unknowns to find than you have the constraints. Sorry?
How much margin we should maintain? Like its condition is P2 much greater than omega.
Yeah, you are given the phase margin also, right? The final goal is, this is what you are given. No one cares about what you do in the design. final target is this. You, for a given CL, you get this phase margin at this, right? So,
To know these quantities, like tan inverse omega u loop by P2 and tan inverse beta GM1 by GM2.
correct.
And P2 is also known. Not
Unknown.
known.
Yeah, both of them are unknown. So what can you do? You'll have to assume something, right? So what can you assume for this? I know GM2 should be greater than GM1. So let me assume to be, let us say, 5 times GM1. Right? So that will set this quantity. So then what can you find from this? I can find what is the location of the pole P2. Right? And once P2 is known, if I look at the expression for P2, P2 is GM2 by CL. I know the load capacitance, so I can find GM2. Once GM2 is known, what can I find? I can find GM1 because GM1 is GM2 by 5. That's my assumption. Okay.
But we haven't used omega u loop.
Yeah, so what is the other thing that needs to be found? CC. Right? So I know omega u loop is beta times GM1 by CC. So from this you will get what is CC.
Minimum what value we have to take? You have taken 5.
I mean, depends, right? I mean, there is no restriction. As you mentioned, the final target is this, right? No one cares how you meet them, as long as you are making some reasonable choice. I mean, don't make it like 1,000 times, 10,000 times. 5 to 10 times, yeah, okay, fine. Right? Okay, so as a designer, your job doesn't typically stop there, because let us say you make this, and what can happen often is, let us say because of some other reasons the requirements change, specifications change or something. Now let us say you have designed this, okay, so you have done this, but then I find that my load capacitance increases. Okay. I want to maintain the same omega u loop and the same phase margin for the same feedback factor beta. So first thing you identify, if CL increases, what gets affected? P2 moves to a lower frequency or high frequency? P2 becomes lower. So what gets affected in the specifications? Phase margin. I mean, I am targeting only these three, right? If CL increases, second pole moves to a low frequency. So phase margin will decrease, because as you see, right? So this means first phase margin reduces. So to restore the phase margin, what should I do? Yeah, I mean, the only leverage I have is to get a particular phase margin, this ratio has to be fixed, right? So which means somehow I have to, I'll write it clearly. If CL increases, the second pole reduces, which means phase margin also reduces. So the countermeasure that you can do is somehow increase P2. And how can you increase P2? P2 is GM2 by CL. So I have to only increase GM2. Is that okay? And yeah, I mean, if you recollect, GM2 is the second stage transconductance, and that we typically will be realizing using a common source. Yeah, because it takes in one input, one output. So it's a single transistor. So if you were to increase the GM without affecting anything, the simplest thing you can do is take an identical transistor, put in parallel. Right? So now if this carries a current I, what will be the total current? And this corresponds to a transistor with a width of 2W.
Basically, you want to make the overdrive.
Yeah. Basically, we are already designed for some operating point voltages. If you don't want to disturb anything, you just put things in parallel. Right? So you basically increase the current and the width at the same time. Again, we'll see some of these later in the class, later in the course, but as of now, this should probably make sense. Okay, so now let's say I give you second scenario. This is, let us say, scenario 1. The second scenario, what I find is my load resistance RL decreases, right? Or I will say the load conductance GL increases. Again, finally, I want to retain all these. First, the job is to go and find what happens when the load resistance decreases. What all changes? I mean, look at expressions here. If the load conductance increases, what all changes? Yeah, my DC gain reduces. Yeah, P1 also gets affected. So basically, my A0 reduces. That is not a great thing. You want a sufficiently large DC gain. And here you see what happens to P1. P1 moves to a higher frequency, right? So what might be the effect of that? Yeah, I mean, in this expression, what will change? See, if you recollect, we assume that the phase added by the first pole was minus 90. That was assuming that the first pole is at a much lower frequency than the unity loop gain frequency. If the first pole shifts to a higher frequency, this might not be exactly 90. So phase margin can take a hit. So what is the solution to this? I mean, if you see, if GL reduces, what actually happens is this ratio changes. It is this ratio that determines everything. So what should I do? Counter is what? I have to increase GM2. Because if you see, the DC gain is basically dependent on GM2 by GL prime. Similarly, the pole location was also dependent on the same thing, right? So only way is to go and increase GM2. Again, you go and increase the current and width, right?
Can't we change GM1?
You can change GM1, but if you change GM1, what else will get affected? Omega U loop gets affected. You can do anything, but
omega U loop will shift further to the right.
yeah, but let us say you don't want to over design also. If you are increasing GM1, I mean, that means that you are increasing power and necessary, right? You don't want to unnecessarily increase this. If you want to retain the same thing, this is the simplest thing you can do. And if you make this observation, when the load capacitance increased, I increased GM2. Similarly, when the load resistance decreased, I had to increase GM2. Does it make sense? Why? So what we found is, whenever the load became difficult to drive, that is when the load capacitance increased or the load resistance decreased, looks like the solution is to increase the second stage transconductance GM2, right? That seems to be the solution. The question is, does it make sense? Why?
Because it's the main task of the second stage to...
Yeah, if you recollect, the main reason to come to the second stage, it's lagging something, should drive the output, right? So this was first stage was giving the gain. Its goal is to go and drive the output load. So if the load becomes difficult to drive, you make the second stage stronger. Okay. So maybe I'll just do one last thing and we'll end. So let us say I find that now I want to increase omega U loop. Basically, I want to increase omega U loop, keeping these guys same. What all can you do? What does unity loop gain frequency depend on? I can either increase GM1 or decrease CC. If I increase GM1, what all will get affected first? DC gain increases or decreases? That is good or bad? So that's fine, right? And if you reduce CC, what all can happen?
Pole 1 can shift to the right.
Pole 1 can slightly come to the right. Yeah, so, right? And also remember, we had made this assumption that Cc is greater than C1. So that probably you should check, right? But when I increase omega u loop, what happens to the phase margin? Omega u loop increases, so this ratio increases, phase margin reduces. So to keep the same phase margin, what should I do? It depends on the ratio of omega u loop and P2. I have to increase second pole, and the only way to increase second pole is so again, this is something one of you asked in the last class. If you want to increase omega u loop, will you increase the power consumption? Again, if you want to keep the same phase margin, you have to increase. If you don't care about the phase margin, it's okay, right? It's free. You can just reduce Cc, no extra power consumption. It's good. So basically, bottom line, whenever you find that something is not working, yeah, basically increase the power consumption, right? So just like in Avengers, how when Thanos snapped his fingers, half the problems disappeared. When you increase power consumption, half the problems typically goes away. But just like how in the movie, that was not the optimal solution every time. Even in circuit design, this is not the best optimal solution, because if you are a good analog designer, you will say that, hey, I know better things to do other than to go and increase the power. Okay. But in this case, at least in this scenario we have seen, seems like increasing power is inevitable, but that might not be the case all the time. Okay. So let's stop here.